Hello, student. Welcome back to this topic of surface tension. So, in this session, I am going to explain how we can determine the surface tension as a function of temperature. So, generally, you know that the surface tension can be measured very easily by a very popular known method called as the capillary rise method. But in most of the cases, what happens in case of the capillary rise method, multiple capillary tubes of different radii are used, and all the measurements are done at a room temperature for a given liquid. So that is why you will not get what happens to the surface tension if the temperature is changed. So the same technique, same experiment I have slightly modified to check the effect of temperature on the surface tension of a given liquid. So it's very simple. In this session, I will explain how it can be done very easily in your laboratory. So that is why the objective of this experiment is to study the effect of temperature on the surface tension of a liquid by capillary rise method. And the apparatus required are you should have a capillary tube, one capillary tube. Only one capillary tube is required. That is very important. As in the normal experiment, you need 3 or more capillary tubes. So in this experiment, you will need only one capillary tube. And experimental liquid, it can be a water or a soap solution or a salt solution, whatever it is. And you need a beaker. You need a beaker to measure, to pour the experimental liquid like water. And you will need a traveling microscope, a needle, support stand and wire mesh is required, and an electric hot plate or heater is required. So these are the things required to do this experiment. Theoretical part. So a molecule well within a liquid is surrounded by other molecules on all sides. So therefore, the surrounding molecules attract the central molecule equally in all directions, leading to a zero net force. However, the resulting force acting on a molecule which is at the boundary level, that means at the top layer, top surface of the liquid, the resultant force is not zero, but points into the liquid. This net force causes the liquid surface to contract toward the interior until the repulsive collision force from the other molecules halt the contraction at the point, generally at the middle of the liquid, when the surface area is a minimum. So if the liquid is not acted upon by external forces, generally a liquid sample forms a sphere which has the minimum surface area for a given volume. So nearly spherical drops of water are ephemeral sight when the external forces are negligible. So the surface of a liquid behaves as though it is covered by a stressed membrane. The surface tension is defined thus as the magnitude of the force exerted tangential to the surface of a liquid divided by the length of the line which is drawn imaginarily over the surface of the liquid in order to maintain the liquid film. So the force is parallel to the surface of the liquid, but it is perpendicular to the line which is drawn imaginarily over the surface of the liquid. So thus, surface tension is therefore measured in units of Newton per meter in SI unit. So that's why in simple way we can say that surface tension is expressed in Newton as a force per unit length. So that is why the SI unit goes a Newton per meter. So it is given by surface tension is equal to F by L. So this diagram depicts or explains the surface tension, the phenomena of surface tension. You can see here, this is the molecule well within the surface. So this is the top surface of the liquid, but this molecule is well inside the top surface. So that is why this molecule is attracted by all the surrounding molecules equally in all directions. Hence, the net force acting on this molecule is zero. But look at the molecule which is on the top of or over the, which is half immersed at the top layer of the liquid. So this molecule is pulled by only the molecules of the water or liquid present inside the liquid. So on the top surface, there are no molecules to attract this one. So that is why the net force acting on this molecule is not zero. So that is why there is some resultant force or net force acting on this molecule, and that net force is acting downward towards the liquid. So this is how what happens, and what happens because of this net downward force acting at the middle down in the downward direction. What happens? It a type of a type of a type of downward pulling action comes here. So that is why the top layer or the film layer formed over the top surface of the liquid is contracted towards the center. So this contraction continues until it is repelled by the molecules which are more accumulated at the center. So this is what happens during the surface tension. Same thing I have explained here. So in this experiment, we're going to determine the surface tension of a water by capillary rise method. So this capillarity is a combined effect of cohesive and adhesive forces that cause liquids to rise in tubes of very small diameter. So this is, as you know, when a capillary tube is dipped into a liquid, the liquid rises into it. So this is called as the capillarity. The rise of the liquid depends upon the diameter of the capillary tube and the magnitude of these cohesive and adhesive forces. In case of water, in a capillary tube, the adhesive forces always draws it up along the sides of the glass tube to form a meniscus. So a meniscus is formed at the top layer of liquid because of this surface tension. So the cohesive force also acts at the same time to minimize the distance between the water molecules by pulling the bottom of the meniscus up against the force of gravity. So this force of gravity will be acting downward, but that is opposed by the molecules present in the liquid. So that cohesive forces opposes the downward gravitational force. So consider the situation as depicted in this figure 2. You look at this figure 2. The figure 2 is redrawn. So here a beaker is there. Inside the beaker you have one liquid, and this is the capillary tube what you have inserted into the or immersed in this liquid. So this capillary, inside this capillary tube, up to this much of height, the liquid is raised. So the surface tension, this force acts tangentially to the surface always it acts tangential to the surface of the liquid. So at the edges, you can see here, this is the direction of the tangent surface tension force acts in this direction. So this force is resolved into two components. This is the horizontal component T sin theta, and this is the vertical component T cos theta. Same thing happens this side also. So that is why these vertical components, that is T cos theta are responsible for the drag of this liquid to certain height inside the capillary tube. But what happens? The rise of the capillary tube takes place until its total weight, which is in downward direction, is balanced by this vertical component of the surface tension. Then once they becomes equal, equilibrium condition is reached, then there will be no further rise of the liquid inside the capillary tube. Thus, at equilibrium, the force of gravity is given by this equation. So where rho is the density of the liquid, h is the height, and g is the gravity, and pi r square is the surface area of this capillary tube, and hence this small r is the radius of the capillary tube. So this is the upward vertical component of the surface tension acts in upward direction. F is equal to 2 phi r into T cos theta. So this upward dragging force balances the downward gravitational force given by the equation 2. And once they become equal, the equilibrium condition is reached. So that is why at equilibrium, the equations 2 and 3 can be equated as below. So this is equation 2 and this is the equation 3. We are equating them. We simplify it. So remember, this is G, this is also G. So I am getting an expression for surface tension T as rho h r g upon 2 cos theta after simplification. And this cos theta can be written, can be equal to 1 when theta is small. So this expression is reduced to this form, a simple form as rho h r g upon 2. So this is the formula to calculate the surface tension of a given liquid. It also be noted that the surface tension of a liquid depends very markedly upon the presence of impurities in the liquid and upon the temperature. Viscosity and surface tension are two rudimentary properties of the liquid. The layers of the fluid show resistance, and that is known as the phenomena of viscosity. And the same resistance that is shown by the surface of the liquid against penetration is known as the surface tension. So the surface of the liquid resists the penetration of the things from its top surface. So that gives the surface tension. As the temperature increases, viscosity decreases. This is a very, very important point. And this is the topic of this session. So what happens? As the temperature increases, viscosity decreases. In simple terms, viscosity refers to the liquid's resistance to the flow. So with increasing heat, fluid starts to flow more smoothly because viscosity decreases. As temperature increases, surface tension decreases. Why surface tension decreases? Because the molecular forces, that is adhesive force and cohesive forces decreases. That is why the surface tension also decreases. Okay. So this is the result of the intermolecular cohesive force decreases and finally surface tension increases. Once the surface temperature is, once the surface temperature is decreased, uh, the capillarity of the liquid, once the surface tension, it's not a surface temperature. Once the surface temperature, surface tension is decreased, the capillarity of the liquid decreases and hence the height of the liquid in the capillary tube also decreases. So this phenomena we are going to prove in this experiment. So this is the experimental setup. You need an electrical heat or generally a hot plot. You can use the things like hot plot or hot plate. So over that you have to use, you have to keep a wire mesh, and over the wire mesh you can keep a beaker containing a liquid. Wire mesh is used to heat the beaker or liquid uniformly and slowly. And inside this beaker, we have kept a C, a capillary tube. So once the capillary tube is immersed into this liquid, the liquid rises to this level. And this is the needle which is hanged in such a way that it's a sharp edge. It's a sharp edge just touches the surface of the liquid. And now, since we are using the heater, we are going to heat the liquid, so temperature changes. To note down the temperature changes, we have to use a thermometer. So a thermometer can be inserted into this liquid. And this is the meniscus inside the capillary tube. And this meniscus is to be watched or seen by this traveling microscope. So this is the traveling microscope. This is the vertical scale, and this is the telescope. And we are focusing the traveling microscope to this meniscus, and we can get some readings. So in this way, in simple way, you can arrange the things so that this experiment is done. So procedure, what are the procedures here? So what you have to do first, fix the supplied capillary tube on the horizontal stand, on a stand horizontally. Focus the trailing microscope to inner diameter of the capillary tube. First on its left side and then on its right side. Therefore, the two readings are gives the diameter, then get the radius. So first we will have to measure the inner diameter of the capillary tube. For that, we have to use the microscope and capillary tube and a stand. Next, keep the glass beaker containing water on the heater. Use the wire mesh. Immerse the capillary tube in the water and fix the capillary tube to a stand. Also immerse a thermometer in the water and fix it to the stand to note down the rise in the temperature. So all these things I have shown here. So stand is not shown here. It makes it just complicated. You can put a stand beside here. To that stand, all these things can be fixed using the clamps. So to the same stand, fix a long needle such that its sharp edge just touches the water surface. So needle is here, I have shown. So this is the needle. So sometimes what happens, if you fix the capillary tube to the clamp of the stand, you can tie a wire to hold this needle. So that also you can do. And focus the trailing microscope so that you can see the inverted or convex meniscus of the water. Adjust the horizontal crosswire to the tangential to the convex liquid surface. Note down the reading, say R1. on the vertical scale. So here, meniscus of the water in the capillary tube is seen through this telescope. So focus the what is that horizontal cross wire to the bottom of this meniscus and note down the reading like MSR, CVD, intertrolling and the least count of the trolling microscope and get the reading. So that is the one reading. Another reading, next move down this trolling microscope down so that you focus the trolling microscope to this tip of the needle, which is just touching the surface of the liquid. Then take a reading. So this is the second reading. So two readings are taken each time. So the first reading R1 is for the meniscus. The next reading is for the needle. So the difference of these two readings gives the height of the liquid raised in the capillary tube. And now switch on the heater and keep it. So whatever you've done up to the step 8 is at room temperature. And now you are switching on the heater to heat the liquid and keep it in a low heating mode because a slow heating is required here. Otherwise, some results may not be good. So once the temperature rises to 10 degrees centigrade from the room temperature, note down R1 and R2 and obtain the H. So this step is repeated for different rise of the temperature. That means we have to do this experiment for every rise of 10 degrees centigrade. And in each case, you obtain H, the height of the liquid inside the capillary tube. Then calculate the surface tension in each case using the equation 4 and plot a graph of surface tension versus temperature and makes a conclusion. So this is the nature of the graph. This is the take the temperature on x-axis and on y-axis surface tension. So it is nearly a straight line. So this line tells that the surface tension decreases as the temperature increases. And what are the observations here? So you will have to determine the inner diameter of the capillary tube. So for that, you need again the traveling microscope. You have to find out the least count of the traveling microscope and get it. Next, this is the capillary tube and focus the traveling microscope to this capillary tube, which is tied, which is fixed to a stand. Then inside the view, use the vertical cross wire and focus the trailing microscope to left side of the inner tube. Adjust the vertical cross wire to left end of this inner diameter of the capillary tube and take the reading. Then move the trailing microscope to the right side and take another reading. The difference of these two readings gives the diameter of the capillary tube and therefore the radius of the capillary tube R is given by it is d by 2. It is a d by 2 and you'll get and express that in meter. So this is how you are determining the inner diameter of the capillary tube. Next part, to determine the surface tension of the liquid. So this table is required. So serial number, the first column will be for the serial number. Second column is for the temperature. And this is TM reading for water meniscus. And this is the TM reading for the needle. So this is X, this is Y, Difference of these two readings gives a height of the liquid in the capillary tube, that is H. Then use this formula T is equal to rho H Rg upon 2, because all are constant here except this H. So H, the value of H only we have to substitute and get the surface tension value. So this is done for the room temperature, and similarly, as the temperature rises by 10 degrees centigrade, we have to note down all the things and calculate the surface tension in each case. And these are the values, expected values for water. The surface tension of the water at room temperature is around 0.073 Newton per meter. And it should be around this value. And as the temperature increases, this surface tension may decrease in this way. So very simple experiment. Easily you can do it in your library. And what is the result of this experiment is that it is confirmed from the last column of the table and plot. That plot means this graph. It is a graph of surface tension versus temperature. From these two, it is clear that the surface tension decreases as the temperature increases, and hence the result. So thanks for listening. I hope that this may be useful for you sometime. Thanks for watching.